Chapter 9, Hypothesis Testing for a Single Population. In this chapter, you will learn to 1. State the null and alternative hypothesis. 2. Distinguish between a one-tailed and a two-tailed hypothesis test. 3. Understand the difference between a type 1 and type 2 error. 4. Understand the role that the significance level plays on the hypothesis test. 5. Perform a hypothesis test for the population mean and population proportion. 6. Calculate and interpret a p-value for a hypothesis test. 7. Calculate and interpret the power for a hypothesis test. This chapter consists of 9.1, an introduction to hypothesis testing. 9.2, hypothesis testing for the population mean when population standard deviation is known. 9.3, hypothesis testing for the population mean when population standard deviation is unknown. 9.4, hypothesis testing for the proportion of a population. 9.5, type 2 error. Section 9.1, an introduction to hypothesis testing. Every hypothesis test has both a null hypothesis and alternative hypothesis. The null hypothesis, denoted by H0, represents the status quo and involves stating the belief that the population parameter is less than or equal to, or greater and equal to a specific value. The alternative hypothesis, denoted by H1, represents the opposite of the null hypothesis and is believed to be true if the null hypothesis is found to be false. The alternative hypothesis always states that the population parameter is greater than, not equal to, or less than a specific value. You need to be careful how you state the null and alternative hypothesis. Your decision will depend on the nature of the test and the motivation of the person conducting it. Suppose the null hypothesis is A0 mu equal to 56 seconds, or the status quo. In this example, we are assuming the status quo is that the internet users spend an average time of 56 seconds on a web page. As a result, this statement is assigned to the null hypothesis. The alternative hypothesis reflects the opposite condition, that the average time is not equal to 56 seconds. Therefore, H1 is mu not equal to 56 seconds. A hypothesis statement can be used only with a population parameter, such as mu, not sample statistic, such as average. The following statement would not be appropriate. It's not. Average equal to 56 seconds is 1 or is alternative, average not equal to 56 seconds. These are not appropriate because we can calculate the sample mean or sample proportion. Therefore, there is no need to perform a hypothesis test to make a statement about sample statistic. The purpose of hypothesis tests to make a statement about the population parameters for which we do not have complete knowledge. Often, hypothesis testing is performed by researchers who want to prove that their discoveries are an improvement over current products or procedures. Suppose a company claims that a new bulb it has developed has an average lifetime that exceeds the current industry average of 8,000 hours. To test this claim, the company would set up the hypothesis as follows. H0, mu less than or equal 8,000 hours. This is the status quo. H1 or H alternative, mu greater than 8,000 hours, or the manufacturer's claim. Note that the alternative hypothesis was used to represent the claim that the company wants to prove statistically. Because of this, the alternative hypothesis is also known as the research hypothesis. Two-tailed hypothesis test. A two-tailed hypothesis test is used whenever the alternative hypothesis is expressed as unequal. From the previous example, H0, mu equal 56, and H1 or H alternative, mu not equal to 56. This is considered a two-tailed test because the alternative hypothesis is stated as a H1 or H alternative mu not equal to 56. This test is shown graphically in figure 9.1. The curve in figure 9.1 represents the sampling distribution of the mean for the number of seconds an American look at a web page. The mean of population, which is assumed to be 56 seconds according to the null hypothesis, is the mean of the sampling distribution and is designed by mu is 0. The procedure for a two-tailed hypothesis test is as follows. Collect a sample of size n and calculate the sample mean. For this example, our sample will be used to calculate the mean viewing time per web page. Plot the sample mean on the x-axis of the sampling distribution curve shown in figure 9.1. If this sample mean falls within the white region in figure 9.1, we do not reject H0. That is, we do not have enough evidence to support H1, the alternative hypothesis, which states that the population mean is not equal to 56 seconds. If the sample mean falls in either shaded region, otherwise known as the rejection region, we reject H0. That is, we have evidence to support H1, which result in our belief that the true population mean is not equal to 56 seconds. One-tailed hypothesis test. A one-tailed hypothesis test involves the alternative hypothesis state as OR. From the previous example, that a company claimed their new bulb average lifetime exceeds 8,000 hours. The null and alternative hypothesis can therefore be expressed as follows. H0, mu less than or equal 8,000 hours. H1 or H alternative, mu greater than 8,000 hours. This test is shown graphically in figure 9.2. Here, there is only one rejection region, which is the shaded area on the right tail of the sampling distribution. We follow the same procedure outlined for the two-tailed test and plot the same mean, which represent the average life of new bulb. Two possible scenarios exist. If the mean sample falls within the white region, we do not reject H0. That is, we do not have enough evidence to support H1, the alternative hypothesis. Our conclusion is that we have no evidence that the average life of the new bulb exceeds 8,000 hours. If the sample falls in the shaded region, we reject H0. That is, we have enough evidence to support H1. We support the company's claim that the average life of the new bulb exceeds 8,000 hours. The logic of hypothesis testing. The only two statements we can make about the null hypothesis are that we reject it and do not reject it. The reason we are limited to these two conclusions is because hypothesis testing relies on proof by contradiction. That is, we assume the null hypothesis is true and attempt to disprove it by finding evidence to the contrary. By using this strategy, we can only conclude that null hypothesis may be true because we do not have enough evidence to say the null hypothesis is true with certainty. Because of this limitation, we can never accept the null hypothesis. The most we can say is that we do not have enough evidence to reject the null hypothesis. We can use the analogy of the legal system to illustrate this point of view further. Because the US court system assumes a person is innocent until proven guilty, the hypothesis test is formulated as follows. Is null. The defendant is innocent or status quo. Is one or is alternative. The defendant is guilty. The two conclusions the court system is capable of are as follows. 1. Reject the null hypothesis. The defendant is guilty. 2. Fail to reject the null hypothesis. The defendant is not guilty. If the members of jury find a defendant not guilty, they are saying the defendant is innocent. Rather, they are saying that there is not enough evidence to prove guilt. A not guilty verdict is failing to reject the null hypothesis. Concluding that the defendant is innocent is a much stronger statement than determining that the defendant is not guilty. However, the court system does not have the capability to conclude innocent, which would be accepting the null hypothesis. In conclusion, there are two things you should never do. Number 1, run with a sharp object in your hand to accept the null hypothesis. After we have covered the basic of hypothesis testing, we need to consider errors that can occur due to sampling. The difference between type 1 and type 2 errors. Remember that the purpose of hypothesis test is to verify of a claim about a population based on a simple single samples. Because we are relying on a sample, we expose ourselves to the risk that our conclusion about population will be wrong because of a sample error. For example, perhaps the null hypothesis is true, but we have been unfortunate enough to draw a sample that is not really representative of the population. Or perhaps the sample is too small or the survey poorly designed. There are many circumstances that can result in a faulty conclusion. Let us use the previous bulb example to illustrate the error with the following hypothesis. Is 0 or mu less than or equal 8,000 hours? Is 1 mu greater than 8,000 hours? Suppose that the sample fall within the reject is null, area region in figure 9.2, that is, according to the sample, the average life of the new bulb exceeded 8,000 hours. But what if the true population mean is actually much less than 8,000 hours? That can occur primarily because of sampling error. The type of error where we reject is not, when in reality it is true, is known as a type 1 error. The probability of making a type 1 error is known as alpha. This alpha is defined as the level of significance. As the tester of a hypothesis, you decide on the race level all alpha. You are willing to accept if you incorrectly reject the null hypothesis. Generally, those performing hypothesis tests select value of alpha ranging from 1% to 10%. Which level you select depends on how critical it is that you don't make a type 1 error. Whatever value of alpha is chosen, it should be determined before the data is gathered. We also can experience another type of error with hypothesis testing. Let us say that the bulb sample falls within the do not reject null hypothesis, area or region of figure 9.2. That is, according to the sample, there is no evidence that the average life of the bulb exceeds 8,000 hours. But what if the population mean is actually much more than 8,000 hours? The type of error where we do not reject is null when in reality it is false is known as type 2 error. The probability of making a type 2 error is known as beta. The value of beta will depend on the value of alpha that is selected. Decision rule for the two hypothesis test error. We reject null hypothesis actually true or type 1 error. Probability of type 1 error equal to alpha. Is null is actually false or correct outcome. We do not reject is null is actually true or correct decision. Is null is actually false type 2 error. Probability of type 2 error is equal to beta. Let us return to our glass manufacturer example to highlight the difference between type 1 and type 2 errors. Recall that at procedures, a glass product whose average thickness needs to be 4 millimeters. If the process average is more than 4 millimeters, the product is acceptable. It's not acceptable. We use the following hypothesis. Statement for the application. Is null mu equal to 4 millimeter? Process is satisfactory. Is 1 or is alternative mu not equal to 4 millimeter or process is not satisfactory. A type 1 error would occur if we reject the null hypothesis and conclude that there is a problem with the process, when in fact the process is working fine. In other words, we conclude that the average glass thickness is not equal to 4 millimeters. We call a type 1 error the producer risk because when it occurs in quality control setting, the producer is looking for a problem in its process that does not exist. That is, the producer is rejecting the good product. A type 2 error would occur if we fail to reject the null hypothesis and concluded that the process was working fine, when in reality the process was having a bad day. Here, we concluded that the average glass thickness was equal to 4 millimeters when it actually was not. We call type 2 error the consumer risk because when it occurs in quality control setting, the customer is getting product from process that is not performing properly. With hypothesis testing, we decide on a value for alpha before we collect the sample. Once alpha has been set, the value of beta can be calculated. Ideally, we would like the value of alpha to be as small as possible.